I'll tell you there. It's kind of silly, isn't it? All right. But most of them are like that. The abbreviation usually incorporates the last thing you'd say after it. Which, whatever. So PET scans actually work by shooting a beam of positrons at the person. Those positrons then are going to go into the person. And in environments where there's a lot of electrons, they'll annihilate very quickly, right? In environments where there aren't a lot of electrons, like there are gaps and things, it's going to annihilate slower. You can also track the three-dimensional direction where it actually annihilated by where the sensors get triggered in 3 dimensions based on that, okay? Like the order they get triggered. Kind of like tracking somebody on a cell phone tower, okay? Is that making some sense? Yeah. Kind of neat, huh? So, if you're wondering, we do shoot people with antimatter beams. That's a real thing. That's not science fiction. And we do it for their health. Which is, I mean, come on. You gotta appreciate the irony of that, right? Okay. So a neutron, this has no charge. It's represented as N for a neutron, and then you put mass 1 and then charge 0. Neutrons are used to cause radioactive decay. Typically, we use them to create nuclear transformations. They are a commonly released byproduct on a number of different decays. For example, uranium decay commonly shoots off 3 neutrons. And so we can go ahead and take a piece of uranium that's purified pretty well. We can go ahead and put that in a lead container, drill a hole into it, and then we have a little neutron beam that we can put other stuff in front of and cause it to undergo nuclear transformations. Okay. In nature, this happens quite a bit actually, because neutrons are commonly ejected from the sun and other cosmic entities, other stars usually. But also black holes. And we get a pretty constant rain bombardment onto our planet of neutrons. Most of these neutrons end up annihilating and doing their nuclear transformations up in the upper atmosphere. Okay? And so this is, for example, why we have like carbon-14 that's in ours right now. And we can do carbon-14 dating. Okay? Okay. So let's talk about the biological effects of radiation. The radioactive emissions contain a lot of energy. They will interact with any atoms, whether or not in a living or organism or dead, or it doesn't matter. Okay? Could be the air, could be you, it could be anything. Okay? We're all made up of the same sort of atoms. They all have nuclei, right? And so a lot of these undergo the same sort of transformations. Alpha and beta particles, neutrons, positrons, gamma rays, and X-rays are ionizing radiation. Anybody ever heard of ionizing and non-ionizing radiation? Okay. So ionizing radiations is types of radiations that will cause ions to develop. Okay? Non-ionizing radiation is stuff that will not cause any ions to develop. Okay? So for example, a typical Wi-Fi router is releasing non-ionizing radiation. Okay? Right now, your phones, you yourselves, and the windows are all directing non-ionizing radiation at you. Right? It's called electromagnetic radiation. It's what light is. Okay? And so typically, ionizing radiation, unless you get very, very powerful. For example, a 5G tower from here will not do anything. Okay? In general, a 5G tower is not going to affect your health in any way whatsoever. Okay? If you were to stand right next to a 5G tower and go ahead and take a nap next to it, it could start affecting your health. Okay? Because it is a pretty powerful source of radiation. It would take a lot of time to really have an effect. If you were to go up and start like touching it, or worse, licking it, or lick your finger and touch it, you would have a very rapid decline in your health. Okay? i.e. you'd get electrocuted. Okay? But in general, you have to be very, very close to a very powerful source of light. Does anybody know what the most powerful source of radiation in this room is? And probably in the campus as well. Because as far as I know, we don't have any Raman instruments or anything. Okay. That light switch. The lights in every room are the most powerful source of radiation in the campus. Okay. Probably not the city, because I believe they actually have a couple pretty advanced labs, and those probably have some powerful lasers in them. Yeah. Okay. So the loss of electrons is usually what this is causing. For example, in the beta particles, that is an electron. And so once those slow down, they will join other atoms and add electrons to them. Okay. Neutrons typically blast things apart and scatter them, and so you end up with positive charges here and there. The gamma rays and X-rays actually cause the electrons in your atoms to jump out of their orbitals and go flying off. Okay? All right, and so this actually is going to cause these atoms to become much more reactive, less stable. And what ends up happening is once you make an atom reactive, it's going to react with the stuff around it, right? If the stuff around it happens to be your DNA, is that going to be helpful? No. Interesting side note, it's actually, the newest studies are showing that it's probably not DNA that really causes sunburn. It's actually RNA. It's damaging your RNA. So, did you guys ever hear that it's DNA, damaging DNA that causes sunburns? Yeah. Yeah. It's almost certainly RNA, actually. So, still needs a bit more research to be completely sure, but it's looking pretty much like that. So the loss of electrons in living cells, this can affect, of course, the cell chemistry. It can affect the genetic material. This can cause mutations in your cells. If it caused the correct mutation, it can actually make the cell start going immortal. Do you know what we call a cell that refuses to die and is now immortal? That's cancer. Okay? That's how you make an immortal cell line, is you selectively give it cancer. Okay? And cancerous cells then become immortal. They no longer accept death commands. They will actually outlive you if somebody was to keep feeding them. Okay? And the problem is they take all your nutrients as well. And so, yeah, they end up killing you, right? Which is awful. All right. So what are some of the other biological effects of radiation? So radiation of higher energy can penetrate further into the tissue, affecting cells located deeper in the body. A lot of this has to do with its ability to slip through the orbitals. Remember, when we're talking about atoms, they're surrounded by electrons in clouds, right? And so it's going to have a lot to do with penetrating through that easily. People that work with radioactive materials typically wear things like heavy lab coats, lab glasses, gloves, may stand behind plastic or lead shields, may take more drastic matters, oftentimes wear some sort of face mask so that they're not breathing things in. People who routinely work with radioactive materials or X-ray will usually wear what's called a film badge. This is to monitor their total exposure. It is literally a Kodak film, camera film. It's literally a piece of camera film in a piece of plastic, thin piece of plastic to block the light out. That's it. And then you can see the color of it. If it changes color, you've been exposed to radiation. They do have a limited use by date, and you're not supposed to wear them after that because they will no longer work properly. To be honest, many facilities, the people that have worked the longest get a bit jaded with the safety procedures and will wear their badges far too long, and then eventually that badge either will not change at all or just goes completely dark one day for no reason. Okay? And when that happens, they actually have to declare an emergency, and they have to actually track down if there was any radiation leakage. So it's like a pretty common thing. They take the safety very, very seriously. Okay, But this is also one of the reasons like why nuclear facilities have not gone down in price in the United States at all. They went up exponentially in price since the 1970s, whereas North Korea, they went down tremendously, exponentially down in price. So, did I talk about the limits of radiation exposure? No? Okay. Do you guys know what the limit of radiation exposure is in the United States on normal times? It's about 4 times the average background, which is actually not a lot, but is a pretty reasonable value. Okay? As far as we can tell, there's actually no negative effects at all. In every study we've ever done, it actually, the people in the study that had that radiation level that was a little bit above the normal average on Earth actually were a little bit healthier. But that's probably just a statistical anomaly. But yeah, there's no effects at all. So low levels, no effect at all. It's called a threshold. You have a threshold for most chemicals, most things, most poisons. Okay. During a nuclear emergency, guess what the threshold is? So if they lose a sample, if they have a badge that says the exposure happened, anybody want to guess what the threshold is for radiation? The current federal policy is no threshold. No radiation whatsoever. Do you know why this is funny? So I told you before, you all are radioactive, aren't you? So by federal law, during a nuclear emergency, they should dispose of you as nuclear radiation, radioactive material. You should be nuclear waste. Because you are a nuclear source, and the exposure limit is 0. Which is why you never, ever make a policy like that, right? You never set no threshold, 0 possible things. Like, by that same logic, should we be able to buy a lighter? No, because somebody somewhere has done something stupid. Right? So, it is just, there's some crazy shit going on there. It's also made it like the entire idea of cleaning up our energy and going carbon free is become completely possible because of that, right? Just whatever. Anyways, hopefully some sort of reason will come into effect at some point. All right. So radioactivity, again, this is the biological effects of radiation. So if we were talking about, for example, an alpha particle, this one has a positive charge. It's the slowest moving. And it's the fattest, okay? It has the most mass of any of them. This actually has the least penetrative effect, okay? And so your skin layers, did you guys know that you have several skin layers on the surface of your skin that are dead? Yeah. Yeah, so normally a normal person, about 4 to 7 layers of skin on the surface of them is actually their dead skin, okay? And you don't actually want to carve all that off. It's protecting the living skin right now, okay? And so you typically would remove like the last couple layers if you want it to look nice, okay? And you wouldn't remove all of it. You can actually remove all of it. If you ever get sodium hydroxide or potassium hydroxide on you, you'll actually turn that skin into soap, okay? And so people actually do that stuff where they take very harsh substances and scrape right. Or they'll use sodium hydroxide soaps. It's terrible for you. Really bad idea. Anyways, so the alpha particles, they actually will be blocked by those dead layers of skin. They'll react with them, but it doesn't matter. It's dead skin. Okay? Congratulations, you got protected. Fantastic. Now, having said that, if alpha particles actually make it in you, because say you breathe something that generates alpha particles, they are very damaging. Okay? But typically, if you're exposed to a radiation source, alpha particles is not going to be something you have to worry about. Okay? Beta particles, beta decay, can be blocked by like a thin sheet of aluminum. So aluminum tinfoil. If you want to wear your tinfoil hats, you could. And it would protect you, okay? It also can be blocked by like a couple pieces of paper. So if you take a few pieces of paper and put it in front of a beta decay source, there you go. You got it. Okay. If you want to be sure about it, you go ahead and take a piece of aluminum foil. Okay. Done. All right. Gamma rays, these will penetrate through lead. Actually, if you only have an inch or so of lead, it will actually penetrate through that. Okay. So it takes either a couple inches, 2-3 inches of lead to block gamma rays, or it takes like 3 feet of concrete. Okay. Neutrons, on the other hand, you need very, very thick concrete bunkers. Okay. There are cosmic particles that are coming out of space that have so much penetrative power and are moving so fast that the only way to even detect them is to wait for them to hit the Earth, pass through the Earth, because they penetrate all the way through, and that slows them down a bit. Okay. But your typical neutrons, if you have a few feet of concrete, that'll do it. More than 3 feet usually. Okay. Typically, you don't need more than 3 feet, though. You just need a couple feet because you put steel in there, right? And the steel will help you out. Okay. But this is very, very high penetration. Okay. All right. Does anybody have any questions about that so far?
What about the posterior? What about the posterior? What about the posterior?
Oh, positron?
Yeah.
Oh, okay. Same as the beta. Yeah. In fact, to be very honest with you, the positrons usually don't make it much of anywhere because there's electrons everywhere around us. Like the air has electrons in it, right? And so you need a pretty good beam of positrons to even make it to a target. And then after that, they don't usually last so long. Because they're kind of like, it's kind of like how long does nitroglycerin last if you play soccer? Not very long. You know, nitro goes off if you hit it, right? And so, or like, how long does Russian roulette last if you use a single shot? Not long, right? Because damn positron's so reactive. Yeah. The only reason the beta particles last anything is because they're so small and they're moving so fast. Yeah. The alpha particles, the only reason they even last as long as they do is because they're 0.2 speed light. And like nuclei are not that uncommon. So it can be a little bit difficult to pull electrons from them. Yeah, otherwise you just have helium being shot out. Just pretty nerd. So how much radiation exposure is too much radiation? These are non-emergency numbers, by the way. So this would be like an average number that you would see just in a normal situation. Okay. The sievert, which is the SV, this is the SI unit. It's used to measure the effect of biological damage. Your average annual dose is 6.2 millisieverts. So millisievert, anybody remember milli? The prefix. That's 1,000th, right? So we're talking about 0.0062 sieverts, right? As your annual dosage. So you have a very small dose of radiation on average annually, okay? But it is definitely not zero. It's a pretty consistent radiation dose. 1 millirem is equal to 1/100,000th sieverts. We're exposed to low levels of ionizing radiation every day. Cosmic rays from outer space, there's absolutely nothing that can be done about that. The planet protects us from quite a bit of it, though. Okay. We have radon gas, of course. I think I talked about radon gas before, right? We're a radon state. We don't test for radon gas. Yeah. Okay. And there's some other naturally occurring radioactive elements. For example, potassium has a radioactive element that's in any source of potassium you ingest, and you need potassium in your diet. And so this is the leading cause of your radioactivity is potassium, typically, unless you're eating something real interesting. All right, so the human exposure to radiation, this has increased 40% since the 1980s. This is mainly due to an increased use of radiation in medical procedures, actually. It has almost nothing to do with energy generating radioactivity at all. So the big sources of radiation that have happened since we have started having understanding radioactivity is number one, and the biggest, is we use it in medical tests. So when you get x-rays done, when you get PET scans done, when you have a tracer put in you, has anybody ever done a medical procedure where they give you an injection or have you drink something? Yeah. So typically those are radioactive isotopes that they use to trace that substance throughout your body. Okay? That's the most common form of those tests. And so all of those accrue radiation over that year, right? Is it enough to actually be meaningful? No, not unless you're getting an x-ray every couple weeks. Okay? Which hopefully nobody's getting. Now, there is one more source of radiation that's kind of embarrassing and funny. Does anybody ever heard of NASA and them blowing up a nuclear reactor in the atmosphere? No? Okay, so NASA once launched a probe that used a nuclear pellet to power it, and they messed up the launch, and it blew up in the atmosphere, and then scattered nuclear material all across the planet. And so that's still happening. The other major event that's happened that increased the radiation of the planet by just a bit is the nuclear weapons testing. That, of course, every time they detonated those first nuclear weapons, and North Korea detonates a nuclear weapon, it releases some of the uranium that did not get used up in the explosion. Okay? And that gets scattered into the atmosphere. If it goes high enough, it gets scattered all across the planet. If it doesn't go high enough, it just gets scattered in the area. Okay? And the United States government did... Okay, so the number that they say is different than the number that's been reported by external sources, but somewhere in like the 100-ish, okay, or several hundred-ish range, where they detonated nuclear weapons to test them out. If we were to detonate our modern plutonium weapons, that wouldn't be much of an issue. They're actually quite clean, okay? They leave very little unused material. But the uranium weapons were very, very dirty. And there's some really nasty stories. Does anybody know about the what happened in Utah and Arizona? No? So they dosed about 500,000 people with nuclear radiation over a 20-year period, constantly from the nuclear weapons testing. People were developing cancers. They knew they were developing cancers. They knew they did it for over 40 years. And they not only didn't admit it, but they tried to cover it up. Please look it up sometime if you get a chance. It's probably created about 400,000 cases of breast cancer. Okay? So they may have killed about 400,000 people from that. So now that I've totally depressed you, let's go ahead and move on. Okay. All right. So let's talk about radiation sickness. So the effects of radiation exposure are going to be dependent on time and dose. This is actually true for any exposure and poisoning event. It's always how long have you been dosed and how much have you been dosed. Okay? If it's low and if it's not long, then yay. You will be in a much better position to survive. Okay? If it's a large dose over a lot of time, that's where things start getting really problematic. Okay? So long-term exposure to low levels of radiation is not as life-threatening as short-term intense doses of radiation. In fact, from every test that has actually been done, and every data correlation that's been done, low doses of radiation over time seem to have either no effect or actually a positive effect on people's health. The positive effect one seems unlikely, but wouldn't be the first time something weird happens. Anyways, so an intense short-term dosage will swiftly destroy tissue in the exposed area. Cell types that rapidly divide tend to be killed off more quickly than the other cell types that do not rapidly divide. because what usually gets damaged, expresses the most damage, is your DNA. Okay? Your RNA is sort of the thing that follows along with that as well. But so that's why the more quickly replicating cells exhibit the damage first, usually. All right, so if we're in 5,000 to 20,000 millirem, what we're going to see is cannot be detected, no change, you're good. Okay? 20,000 to 50,000 millirem, you'll have a temporary decrease in white blood cells. WBCs is the abbreviation for those. It'll become a little bit harder for you to fight off infections usually. Okay? 50,000 to 100,000 is going to be mild radiation sickness. This is going to be a very large decrease in white blood cells, nausea, vomiting. This is what you probably have heard about in terms of like, anybody ever heard of like treating cancer with radiation exposure? Yeah. So these are the sort of doses we're riding along. Okay. And the reason you're doing that is, do you know what any cancer treatment involves? There's basically only one type of cancer treatment that we have successfully deployed. We're starting to deploy another. There's actually another where you use the immune system to start targeting different types of cancers, but it's very experimental and we haven't really deployed it yet. But so most radiation, most treatments for cancer involve killing the cancer cells slightly faster than killing the person. Okay? And that's because cancer cells ultimately are your cells, right? And so anything that kills the cancer cell is also going to kill you, okay? It just is that way. Now, cancer cells are a little bit different in the fact that they're always grabbing more nutrients to keep growing. And so that's typically where we target them, is by targeting the fact that they're taking in a lot more nutrients than the other, and so a lot of poisons they take in faster. And so they get larger doses. So that's why like cyanide, radiation, these are all used to treat cancer, right? Yeah. Okay. So right here is 100,000 to 200,000. This is going to be light radiation poisoning. You'll have the delayed appearance of appetite loss, nausea, diarrhea, hair loss, spontaneous abortion in pregnant women, and typically recover in 3 months. This will be like a late stage radiation treatment if they really had to go a long time. Okay? And so this would be 200,000 to 300,000 millirem. This is going to be what's considered moderate radiation poisoning. You have hair loss, fatigue, general illness, permanent sterility as possible. Recovery typically takes several months to recover from if you're going to recover fully. 300,000 to 400,000 millirem exposure. This is an LD50. Do you guys know what an LD50 is? Lethal dose for 50% of the population tested. Okay? So 50% of the people that get this exposure likely would die. Right? Okay. So again, half the population would be dead within 30 days if they were exposed to this dosage. Okay? Okay, so how is a nuclear decay equation written? Anybody know what the most radioactive resistant animal is that's been found? Or complex animal, I should say. Huh? Close, but it's not quite. It's cockroaches are very resistant to radiation. Several thousand times more resistant than a human. But the dung beetle... The dung beetle is 10,000 times more resistant than a human to radiation. So, all right, so how is nuclear decay equations written? This is a nuclear decay equation. So you have the reactants on the left side. Those reactants are going to have the mass up here, the atomic number right here. And then they'll have the symbol. This will then yield. The yield is a way of representing that this equals, right? This gives us those things, okay? And so because it's like an equal sign, we always have to balance each side, don't we? Okay? And so we'll have products that will be on the right side, and those products will have their mass numbers and atomic numbers. there's something that's really nice about these. Because they always list these numbers on them, they always have to balance. So, the mass numbers on the reactants and product sides always have to add up to be equal. Okay? So see how this is 238? This one's 234 plus 4, right? Which is 238 again, isn't it? Yeah. This one right here is 92. This over here, products, is 90 plus 2, isn't it? That's 92 again. Okay? And so nuclear equations are super easy to balance. Very quick, very easy, because they always have to add up on each of those lines, right? The masses all have to add up. The atomic numbers all have to add up. The atomic numbers are actually a representation of the charge. Okay? So for example, an electron has a -1 atomic number, doesn't it? Okay? A proton has a +1 atomic number, doesn't it? A positron had a +1 again, didn't it? Okay? So all that is you're just balancing out the charges, you're balancing out the masses, aren't you? Okay. Anybody have any questions about that? Okay. If it's a decay, it's always going to be a radioactive nucleus, falls apart, we make a new nucleus, and we have some sort of radiation come out. Okay. If it's a transformation, then we'll have some stuff coming together, and that will give us some new stuff. Okay. If it's a fusion, which is like what's done in the sun, things come together, give us a bigger nucleus. All right. So let's go ahead and write out some nuclear decay equations for radioactive emission. So a beta decay and positron emissions. In a beta decay, you're going to have a high energy electron emitted from the nucleus. You'll have a neutron that becomes a proton, and so the atomic number ends up going up. This is actually much easier than it sounds, because the electron would have a -1 here, and that means that number has to go up, doesn't it? Okay. A positron is going to be just like a beta decay, except the opposite signs, right? Yeah. This is a gamma ray or gamma decay. They're only energy, and so what you'll see here is there'll be no difference in these numbers, because a gamma ray has 0 mass and 0 charge. So it doesn't change anything about that. All it is a higher energy nucleus goes to a lower energy state. You can kind of, again, think of it as the nucleons, the protons and neutrons are unstable, and they collapse down and make some noise, right? Okay? And this is the noise right here, which is a gamma ray. So let's go ahead and talk about producing radioactive isotopes. Some isotopes, radioactive isotopes, do occur in nature. A lot of what we end up using is actually made in labs. A lot of those are actually made in what's called radiation wards on hospitals. You ever seen that part that's in the basement, right? That has a little radiation sign on the hospital? Okay. Who here's been supposed to have been there? No? Who here's just accidentally ended up in the area? A lot of you? Yeah. So that should theoretically be the highest security area in the building. They have radioactive materials that could be used to make dirty bombs and stuff like that. But oftentimes the security is not necessarily amazing. So I have both meant to be there and ended up wandering into places I should not have been. So, but I've also been in a bioweapons lab by accident too. So, yeah, I don't know. People let me into buildings. Yeah, they shouldn't. All right. Now, when we produce a radioactive isotope, typically what we're going to do is we're going to take a source of neutrons. We're going to shoot neutrons at a isotope that we want to change. So, for example, we take some MO, molybdenum, and we shoot neutrons at it. And what ends up happening is we actually end up having one of the neutrons stick. And that's going to make a new isotope of MO that is likely radioactive. And so we could be making a positron source, we could be making a beta source, alpha source, whatever we want. Okay? something that will give off gamma radiation. So we get little gamma bursts that slowly happen, and we can follow it as it moves through your bloodstream. Okay? Lots of different options. Radioisotopes can be prepared by bombarding stable isotopes with fast-moving alpha particles, protons, neutrons, usually the things that have some mass to them. Beta particles wouldn't do you a lot of good because it's just an electron. There's other ways of doing that. Okay? Gamma rays also would not do you any good. The ionizing radiation is going to appear on the reactant side because you're shooting it at and getting it to react with it. Mm-hmm.
What would happen if we shoot like a beta particle? So we were shooting like an electron to the atoms. So what would happen?
So, okay, there is something called K-capture, which is where you capture an electron. But that's not a beta particle that causes that. What ends up happening is if you shoot something with a beta particle, it either is just going to penetrate right past it because it's moving too fast, or if you get it to slow down, it's going to make an ion. And so you'll just get something with a -1 charge.
Okay, so like the atomic mass will go down? Or
Nope, atomic mass won't do anything.
atomic number, my bad.
Nope. Nope, because it won't even get to the nucleus. Yeah. Most of the time, beta particles just don't have enough mass to penetrate through. And you have to remember, atoms are usually shielded by electrons, right? They're in those orbitals. Yeah. And so when the beta particle comes through, either it misses the other electrons and just keeps going, or what usually happens if it's actually going to do something, is it's slow enough that repels and ends up getting caught by something. And so it just ends up being just like you had put some extra electricity in the system. Yeah. Yeah, it has surprisingly little effect. Positrons usually accomplish the same thing. So a positron slows down enough, it's going to just hit one of the electrons, they'll annihilate each other and go to energy. And then you're short an electron. Got some energy. Probably a really expensive way to get energy, but yeah. Let's talk a bit about radioactivity units. Now, anybody ever done anything with Fallout, the video game series or movie series? Yeah? Great like show slash video game series. And so you kind of know some of this terminology already. Because the Fallout creators actually did a pretty good job at the original games of incorporating actual science. So, surprisingly good, actually. So the amount of radioactivity present in a given isotope is going to be measured with a number of radioactive emissions or disintegrations that occur per second. Essentially, how many times does it do that per second? Okay. The unit for measuring disintegrations per second is the Curie, and this is abbreviated CI. This is actually named after a Polish scientist, Marie Curie. Anybody ever heard of her before? Okay. Actually an interesting character if you ever get a chance and you want to watch like a documentary. She and her husband did a bunch of discoveries together. They were a really awesome team. And then she was the smarter, more creative one. And that never was a problem, even in her age. So it was kind of a cool thing. Her husband died earlier than her, so she continued publishing and creating after that. So they actually studied radioactivity in France at the turn of the 20th century. They also, Henry Becquerel was the other major scientist that was doing these things. So the SI unit for measuring disintegrations is actually called the Becquerel, and abbreviated BQ, and that's the Henry Becquerel abbreviated one. The activity of an isotope actually defines how quickly or slowly it emits radiation. So if something's very reactive, it will emit radiation very fast. Okay? If something's not very reactive, it will emit radiation slowly. And when I'm saying fast and slow, it could be so fast that you would have half the population disappear in nanoseconds. Okay? Faster than we could even detect All we see is comes together, boom, gone. Okay. It could also be so slow that in 1 billion years, you'll still have half the population. Okay. It could be either one. We actually have a number of radioactive isotopes on the planet that are very slow. And this is why, for example, our core of our planet is hot. That's actually radioactive decay occurring over time. It's been happening for billions of years. And that energy gets trapped in the planet and stays there and builds up. Okay? So this right here is some of the different radiation units and some half-lives. Becquerel, again, 1 BQ. This is a disintegration per second. Curie is 3.7 times 10 to the 10th disintegrations per second. You can really date the ages of these things by the fact that it's like not a mole or anything. That it's just weird number right here. This right here is a millicurie, and that is, of course, 1,000 millicurie is 1 curie. And this is microcurie, which is that little U-looking symbol. And that's 1 million microcuries is 1 curie. Okay, so let's talk about half-lives. So every radioactive isotope emits radiation at different rates. The unstable isotopes emit radiation more rapidly. The rate of decay is going to be measured as the half-life. And that's the time it takes for 1/2 of your atoms in the sample to decay, and you only have half of your sample remaining as the original radioactive isotope. And so this is also known as a physical half-life. The rate of elimination from the body is actually known as a biological half-life. So you would eliminate half of that substance in that amount of time. It's how long it takes you to get rid of half of that substance. The biological half-life shortens the physical half-life. This actually leads to an effective half-life for medical isotopes. So you have 2 ways that you get rid of medical isotopes. If you give somebody glucose that's labeled with a isotope so you can follow it through their system, they're going to do 2 things. You'll have the isotopes breaking down, and so your population decreases as time goes on. That is the physical half-life. You would also have that person breaking down the glucose and then urinating the products out. And that would be the biological half-life. Okay? And together, these things are going to give you an effective half-life. How long that substance is in their body, and it effectively takes them to reduce the population down to half. Okay? The decay is usually measured by something like a Geiger counter. Geiger counters is the one you guys have all probably seen on movies or something. Okay? You guys ever seen where they take like the little wand and it goes click, 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 click? And they get closer to the radiation source and it goes faster. Click, 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 click. Pop, 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 pop. Okay. Okay, that's a Geiger counter. All right, so the half-life. Natural radioisotopes have long half-lives. That's why they're still around. Radioactive isotopes are used in medicine, have shorter half-lives because we don't want to wait for 1 billion years or even 1 million years for us to have a noticeable signal, do we? What would you say to your doctor if, okay, we can see a change, but you have to stay there for 10 years? We'll monitor you for 10 years. That's not going to do you a lot of good, is it? Okay. And so medical isotopes typically have half-lives that are on the order of like days. Okay? They give off radiation pretty quickly. On the other hand, here's some naturally occurring isotopes. This is hydrogen-3. That's tritium. That's the hydrogen with a mass of 3. Okay? So 1 proton, 2 neutrons. Anybody ever heard of tritium before? No? It's becoming kind of more widely reported in the news and stuff because for several reasons. It's one of the ways you can make a fusion reactor, and fusion reactors are something that we're trying to do, right? And it's also something that if we find it on the moon, we think we can find it on the moon, we could have like a moon base, and we're trying to set up a moon base, right? Everybody knows we're trying to set up a moon base, right? Okay. Anyways, so Carbon-14, this has a half-life of 5,730 years. So if I start with 1 gram of carbon-14, how long is it going to take me to get 2.5 grams? One half-life, right? Or 5,730 years. Okay, how long would it take me to get to 0.25 grams? So I halved it, and then I halved it again, right? And so that would take me 2 half-lives, or 11,460 years, right? Okay. Okay, so this right here is uranium-226. It takes 1,600 years for half of that to disintegrate and go to its daughter isotope. Uranium-238, you may have heard of uranium-238 a fair amount. That's one of the more common radioisotopes that we talk about when we talk about nuclear reactors. That is 4.5 billion years. And that's why there's quite a bit of uranium-238, and that's why it's used for making energy and stuff. Okay? It has a long enough half-life that it tends to stick around. Okay, this is some of the radioisotopes that are used in industry, in medicine. You'll notice they have much shorter half-lives, typically in the days, but it could also be minutes. So right here we have like chromium-51, and that's 28 days. By the way, if these half-lives have these, look at that half-life, 110 minutes. Can you make that and just store it for a month? No. That's why the hospitals typically have irradiation wards. It's actually a lab for them to make certain isotopes on larger hospitals. Okay? Smaller hospitals don't have that. They just have a radiation storage unit. And so the only ones they could do is things that have like almost a month-ish, week-ish numbers, right? And they actually have to get it delivered, within a few days usually of you doing the test. They can't just store it indefinitely. Oh, we have it from last year. That's not going to work out well, right? Because it's going to half every single one of these half-lives. Okay? This right here is your effective half-life. Notice they are smaller. And what this is it's your body actually getting rid of that isotope over that time. Okay? And so that's how quickly this stuff moves through your body in terms of what they're using it to label and the isotope it is. Right? Okay, so whenever you work with half-life problems, step 1 is typically to determine the total number of half-lives. It's usually easiest to just do number of half-lives. Remember how I did that where I was talking about the number of half-lives that passed for that carbon-14, right? Okay. And it had 2 half-lives. Let's determine the amount of the isotope remaining from that number of half-lives. So this is actually the equation. Now, honestly speaking, you don't actually have to use the equation. Most people don't bother using the equation. But this is the equation. It's the same compounding equation you would have seen in like your high school level algebra. Okay? And so an isotope remaining is going to equal 1/2 to the n power times the starting number. N is the number of half-lives that have passed. So nuclear radiation, these can be high-energy particles of high-energy rays. Some radioisotopes of elements are going to be useful in medical imaging, as they're going to concentrate in particular tissues. Emitted radiation from those locations in the body can create an image on a photographic plate, or they can be detected by scanning sections of the body. They don't do photographic plates much anymore, but that's how they used to do it. They would literally take photographic plates, let them develop, same as you would like a camera, right? Okay. Nowadays, they usually use detectors that are electronic, and so we can do it much faster or more times to give it more resolution. Okay? And so this right here is one example of that. Okay. What are we seeing when we see these blue dots versus the red dots, by the way? So this is where the radioactivity is concentrated, right? And then these zones will be where the radioactivity is decreased. Okay? Okay. All right, so it's going to be important to expose patients to the smallest possible dose of radiation for the shortest time period possible. Remember that negative effects are directly proportional to the length of exposure and the amount of exposure, right? Okay. So the two main uses of medical isotopes is going to be diagnosing disease states and therapeutically treating disease states. When you diagnose a disease state, a minimum amount of radioisotope with a short half-life, this is going to be called a tracer, is administered, typically attached to something important, though not always. For example, iodine can be directly used because you use iodine in your diet and incorporate it into things like your thyroid. Okay? On the other hand, for example, they oftentimes use radioisotope tracer glucose. So they give you glucose that has radioisotope on it. They follow that glucose through your system. Wherever the glucose gets concentrated is where you're using the most energy. Okay? It's a very convenient isotope to look at brain function. Technetium-99m can be used to diagnose the proper blood flow through the lungs, for example. And so right here we actually have this. This is the normal lungs right here. They may know what we're actually looking at. So these are actually cold spots, right? And we're looking at lungs which have empty spaces in them, right? Okay? So they have bronchus and then empty spaces in between. And so here we actually see these are cold spots where we shouldn't see this. Okay? Right there. Right. One of the things you have to remember is if you're looking at a photographic plate, which parts are the parts that turn white, like the other color, usually? The parts with exposure, right? Okay. So if there's a non-functioning area in the lungs, the tracer's not going to be distributed in this area because you won't have blood flow and uptake from the cells. And it's going to show up as a cold spot. And usually high areas of activity are going to be places which the blood is being detained too long in the lungs. And it's going to show up as hot spots. And so they would be these very bright spots on those lungs. Okay. Areas with rapidly dividing cancer cells will also retain extra tracer because cancer tends to take up more nutrients than other cells and continuously does so. It's not controlled like most cells would be. And so they typically show up as hotspots. And that's why if you've ever seen a cancer diagnosis, it usually has like a dark space and then little spots that are little cancer tumors, right? Okay. Okay. And so radioisotopes can also be used therapeutically, typically to destroy a diseased or cancerous tissue where we're specifically targeting them, in which case we're actually specifically trying to poison them without poisoning the rest of the human. Okay? So for example, iodine-131, this is a beta emitter. It can be administered in a dose that's 1,000 times higher than that of a tracer that would be used to detect the disease. This would poison the human you give it to, but it will poison the cancer more, right? Okay. And so if you very carefully administrate this over a given period of time and carefully monitor the patient's reaction, you can use it therapeutically to destroy, say, thyroid cancer. Okay? Cells that are rapidly dividing are much more susceptible to ionizing radiation. So cancer cells, which rapidly divide over normal cells, right, are much more susceptible typically. And this is because their genetic material is exposed more often during that cell division. When they copy the genetic material, they have to unravel it to read it. And so it has a lot more surface area than your genetic material in a normal cell that's not dividing, which is usually tightly wound up. That's very little area to impact. Okay? And so that genetic material is much more exposed to radiation than it would normally be. Okay? All right. So let's go ahead and talk about, again, some more on the radiation and external beam radiation therapy. So this is where you use gamma radiation, typically generated from cobalt-60. We aim that at a tumor to destroy the tissue. Typically, this has a 3-beam setup. Anybody know why you'd want to do multiple beams instead of one? Okay. So if I shine a flashlight and I try to hit somebody like you at the end, right? Okay. I might catch her too, right? Whoops. Got the wrong one, right? But what happens if I take 3 beams instead and I shine them from 3 different directions? I can have much weaker dosages for anything I accidentally hit, right? And I can concentrate that dosage on one spot in space, right? And this greatly limits my damage to everything else while increasing the damage to what I'm targeting, right? Okay. They do this a lot with ultrasonic as well. It's a more expensive, harder setup, though, as well. And much more targeted, so they have to be more careful with the targeting. They have to understand it better. So in brachytherapy, small titanium seeds containing radioisotopes are actually implanted in the tumor. And so you literally have a radioisotope encased in metal, and you take that radioisotope, you guide it to the tumor you want to get rid of, and thunk, nail it in there, okay? And if you want to do multiple tumors, you'd have to nail those in to the tumors. And what will end up happening is the radiation from those will slowly kill off the tumor. Now, this would usually leave behind these rods, and so normally you would have to go back in and retrieve them, okay? Though I do kind of wonder the amount of damage it would cause to leave the rod in. That would be interesting, a long-term study to see what sort of damage that does, but I don't think anybody's going to volunteer for that one. So, yeah. This is a PET scan. These are positron emission tomographies. There's going to be used to identify functional abnormalities in tissues and organs, typically. Fluorine-18 is going to be present as one of the tracers that's used for a PET scan and has a half-life of 110 minutes. This is one of the things that really limits these scans, and one of the reasons why the hospitals have to very carefully rotate people through. Okay. The fluorine isotope is going to emit a positron as it decays to form oxygen-18. The positron is going to come in contact with an electron, and the gamma radiation is going to be produced. It's then going to be detected by a scanner, so we can narrow down the 3-dimensional where it happened. So this type of scan is typically used for the brain because it has a very low dosage of radiation. It's very targeted, and we can look at where we're having a lot of activity. Okay? Typically, this fluorine-18 is attached to something like a glucose. And so you would be monitoring how much glucose you're using. Glucose is the only form of energy your brain uses. And so that would then tell you how much energy that part of the brain is using. If you have parts that aren't using any glucose, guess what that means about them? Why would tissue not be using energy? It's dead. Yeah. Yeah. Or very close to. Yeah. Yeah. Okay, this is the study guide right here. And I'm going to call that a day because my timing was almost perfect, huh? Yeah. Okay. Does anybody have any questions? Nothing? All right, fantastic. Please go ahead and practice the problems. Also, if you have any questions all about the problems, please contact me and let me know, okay? Okay. All right. Have a good one. Let's end it.